If you know what a phase diagram is, this is probably the type of phase diagram that you're used to seeing. Based on what temperature and pressure are, it tells you whether the substance is a solid, liquid, or gas. This type of phase diagram is important, but in material science, we are not too concerned about the gas phase of the substance and not too concerned about the change in pressure. So what type of phase diagram do engineers find useful? Let's start with something that you have probably experienced. Let's say we start out with a glass of water. Then you start to add sugar, a little at a time. At the beginning, the sugar will dissolve in the water, and you have sugar water. This is all one consistency, so we call it a single-phase liquid. But if we continue to add sugar, there will be a point where no more sugar can be dissolved into the water, and the sugar will precipitate to the bottom of the glass as a second phase. Now we have two phases, a liquid and a solid. But what if we heat the water? Well, the sugar will dissolve and we will end up with a single-phase liquid again. If we cool it down, the sugar will precipitate out, and we will have two phases. Let's see what that looks like in a phase diagram. Take a look at this phase diagram. The vertical axis is temperature, and the horizontal axis is composition. Composition means the amount of water and the amount of sugar. It always adds up to 100%. So if there is 70% water, there is 30% sugar. What does this phase diagram tell us? Let's reproduce what we already know on this phase diagram. Let's start out with 100% water and add sugar a little at a time. At the beginning, the sugar will dissolve in the water, and we will still have a single-phase liquid solution. That means it is the same throughout. But if we continue to add sugar, there will be a point where no more sugar can be dissolved into the water, and the sugar will precipitate to the bottom of the glass as a second phase. We have crossed the solubility limit. Now we have two phases, a liquid and a solid. But if we heat the two-phase mixture up, the sugar will dissolve, and we will end up with a single-phase liquid. If we cool it down, the sugar will precipitate out, and we will have two phases again. This is actually the principle behind precipitation hardening, cooling a metal down so that a second phase precipitates out. Funny, isn't it? You just learned about heat treatment from a sugar-water mixture. We usually talk about phase diagrams in the context of metal alloys. A metal alloy is simply a mixture of two or more metals. We will keep it simple for now and just talk about alloys that contain two metals. For example, we can add nickel to copper to make the copper stronger, or we can add carbon to iron to make the iron stronger. Do you think all metals act like the sugar-water mixture we discussed? I mean, do you think that if we start with iron and keep adding carbon to it, that a second phase would precipitate out when the iron could not dissolve any more carbon? In the case of steel, this is true. Carbon has limited solubility in iron. But it's not true for all metal alloys. For example, copper and nickel have unlimited solubility. That means they are kind of like water and alcohol. No matter how much alcohol you put into water, you will still only going to have one phase. It's the same for copper and nickel. No matter how much nickel you put into copper, you are still only going to have one phase. So what makes one alloy have unlimited solubility and the other not? Well, there are 4 conditions that both of the atoms have to satisfy in order for an alloy to have unlimited solubility. 1. They have to be roughly the same size. 2. They must have the same crystal structure. For example, both copper and nickel have a face-centered cubic structure. 3. They need to have the same valence. That means the number of electrons available for bonding. And 4. Their electronegativities should be similar. Copper and nickel are right next to each other on the periodic table and therefore have similar electronegativities. They differ by only 0.1. Let's look at a phase diagram for copper and nickel. This type of phase diagram is called a binary isomorphic phase diagram. Binary because there are only 2 elements, and isomorphic means to have the same form. So in this case, under normal circumstances, only one solid phase is formed. Let's say that we have an alloy that is made from 60% nickel and 40% copper, and it's heated to 1100 degrees Celsius. What phase would we have? We would have a solid. We call this the alpha phase. Okay, so what if we have an alloy that is 60% copper and we heat that up to 1400 degrees Celsius? What phase would we have now? We would have liquid. So we have a solid region and a liquid region, but what is that region in between? This is the region where there is both liquid and solid. The metal is melted a little bit, but not all the way yet. Let's go back to the first point. The solid with 40% copper, and heat it up. At what temperature will it first start to melt? It melts at just over 1300 degrees Celsius. The line that separates the solid region from the solid liquid region is called the solidus line. Now let's keep heating. At what temperature will it be completely melted? Approximately 1350 degrees Celsius. The line that separates the liquid region from the solid liquid region is called the liquidus line. Sometimes when we have a point inside the solid liquid region, let's say point A, we would like to know the following. What is the composition of the liquid and what is the composition of the solid? Yes, that's right. You may be thinking, since we started with a 60% copper and 40% nickel alloy and heated it up until it started to melt, that the liquid and solid would both have that composition. But let's take a look. When does this alloy start to melt? Around 1230 degrees Celsius. And the melting temperature of nickel is 1453 degrees Celsius. Wait, what? Then how can it melt? Because the melting temperature of copper is only 1084 degrees Celsius. So there is going to be a lot more copper in the liquid. Okay, so how can we find the composition of the liquid and the solid? Look at the figure on the left. You will draw an isotherm line, a line of constant temperature between the liquidus and solidus line. Then drop a vertical line down on both sides. The composition of the liquid is where the vertical line coming off the liquidus line hits the horizontal axis. And the composition of the solid is the vertical line coming off the solidus line, where it hits the axis. See, the liquid contains more copper. The second thing you might want to know is how much liquid and how much solid there is. Answer this question first. Is point A closer to the solid region or the liquid region? It's closer to the solid region. Therefore, there will be more solid than there is liquid. The amount of solid depends on the ratio of the length of this line over the length of this line. And then the liquid is just 100% minus how much solid there is. This is called the lever rule. But how do you know which line segment to use on the top of the ratio? That's why I asked you to answer the question about if there is more solid or liquid first. We know there is more solid by the position of the point. Therefore, we use the longer segment. Do you think if we started with a 50% nickel and a 50% copper liquid alloy and cooled it very slowly to a solid, that it would turn out to be the very same type of solid as if we cooled the same alloy very rapidly? It turns out that the speed at which you cool the liquid alloy down makes a difference. Remember at the beginning of the video when I said that under normal circumstances, we will have a single phase solid in the alpha region? Well, it turns out that if you cool the liquid rapidly, or what we call quenching, you can create a multi-phase solid. Remember the difference in the melting temperature of copper and nickel? Copper melts at 1084 degrees Celsius, and nickel melts at 1453 degrees Celsius. So, which one is going to solidify first upon cooling? Nickel will. So there is an imbalance. If we cool the liquid very rapidly, the first solids that form will have a high nickel concentration. Then each successive solidification will have a slightly lower nickel concentration. But if we cool the liquid slowly, there is adequate time for the phase composition to balance out through diffusion and retain a single phase solid. We will be looking at that in more detail. But first, let's see what copper-nickel alloys are used for. Copper-nickel alloys are used in a wide variety of applications, such as marine applications, because copper has a resistance to biological growth. Thermocouples, because copper has a high thermal conductivity. And coins, because copper has a resistance to corrosion. Adding nickel to copper increases copper's strength and durability. But we can even affect the alloy's strength by the way we process it. Cold working is one way we can change the properties of a metal, and how we cool the alloy is another way. Okay, back to the phase diagram. Let's cool a liquid that is made of 50% nickel and 50% copper. We will cool it first very slowly and see what happens, and then cool it fast and see what happens. Let's first see what happens if we cool the alloy slowly. We will start with a liquid that is 50-50. Then very slowly, we will start to cool it. When it crosses the solid-liquid region, some solid will form. Let's stop at the point indicated and see what the composition of the liquid and the solid are. We see that the solid is approximately 58% nickel, and the liquid is approximately 46% nickel. That makes sense. There should be more nickel in the solid because nickel has a higher melting temperature. Okay, let's start cooling again and stop at the next point. At this point, the solid has approximately 53% nickel, and the liquid has 41% nickel. So how did the solid go from 58% nickel to 53% nickel? The answer is diffusion. Remember, we are cooling very slowly and allowing the metal to reach an equilibrium state through diffusion. On to the next point. When the metal is cooled further, the alloy will again go back to being 50-50. That's what we started with, but only if the cooling rate is sufficiently slow to allow diffusion. In this case, the only strengthening mechanism at work is alloying. Now, what if we cool the alloy quickly? Let's start again with a 50-50 copper-nickel liquid alloy. But instead of cooling it slowly, we will cool it fast. Let's say we cool the liquid so it just touches the solid-liquid region. In this case, the liquid will still have a 50-50 composition, but the first solids will have a 62% nickel. Again, that makes sense because nickel has a higher melting temperature than copper. So we would expect the first solids would have high nickel. Let's cool it some more. At this point, the solid will have 58% nickel. But because we are cooling the alloy down fast, the first solid will remain and the second solid will form around it. Diffusion doesn't have time to balance the solid phase, and we end up with multiple phases. If we cool the alloy to just inside the solid region, our final solid will form. This solid will have a different composition than either solid 1 or solid 2. In the end, you have a multi-phase solid. In this case, there are two forms of strengthening going on, the original alloying and the multi-phase nature of the solid. This is a form of heat treatment. Quenching a metal like this usually makes it stronger and less ductile. What I presented here is idealized. What really happens is slightly different. For example, because the composition of the solid is not allowed to reach equilibrium, the shape of the solidus line will not be as shown. It will be dependent on the cooling rate. Therefore, the compositions and the temperature of the final solidification may change. Also, I presented a three-phase solid, but you can have more or less than that. It really depends on how fast or slow you cool the alloy.